Welcome if you are here at International House, welcome to the IAS, and welcome if you are just beginning to join us on the Zoom space, which I can see is beginning to happen. My name is Marcia Meskimen. I'm the Director of the Institute of Advanced Studies, and it's a great pleasure to welcome you both virtually and in real life today for this seminar. If you are joining virtually, let me give you a little tiny bit of housekeeping really before we get going, which is that you will find on the bottom of your screen both a chat and a Q&A. And you are very welcome to join in to make comments and questions during the course of the seminar by using either of those two interfaces, and we will ensure that those are fed in to the discussion at the end. In addition, your comments in the chat and things like that will not be recorded or maintained, so there's no question about being able to ask questions and then thinking that you have somewhere in the ether you have permanently had those questions recorded. That's not the case, but we will be recording the talk today, and it will be available on the IAS video library probably within a week of today. So if you do want to have a chance to listen again to it, or indeed to share it with people who were unable to attend, you're very welcome. So without further ado, it's my great pleasure that we are welcoming today Dr. Junior Nomani, who has joined us from Auckland University of Technology and who's been a residential fellow with us now for about 3 weeks. Yes, about 3 weeks. And Junior joined us and has been a wonderful fellow. Also really had a very interesting time joining us right in the middle of the theme week for gestation. So we had a lot of really interesting and quite unusual shared conversations that way. But while Junior is here, he is really working with my colleague Mazhar Mohammed, who is in the design school, who is actually going to talk more specifically about their work on additive manufacturing and various kinds of technological implications for that, and a little bit about their shared research project, which, as I understand it, has been actually operating for quite some time. So without further ado, if I can turn to you, Mazhar, and ask you to introduce Junior.
Yeah, thanks, and hello everyone. I can't see a lot of you, but I'm sure you're all there. So I'm Dr. Mazhar Mohammed over in the School of Design and Creative Arts, senior lecturer there in digital fabrication, but wear many different hats, quite multidisciplinary in my work, but I'll leave that for another day. Today is all about my colleague Junior. So Junior is also a senior lecturer in the School of Engineering, Computer and Mathematical Sciences at Auckland University of Technology. However, in another life, we were colleagues together at Deakin University in the School of Engineering there before we parted ways, him to Auckland, myself to the UK. He is also one of the academic advisors for the Maritime Bachelors of Engineering Honours Programme, which he quite modestly put in here, but equally for that, I'm going to shame him and let you all know he was a recipient of a teaching award as well over at Auckland University of Technology for excellence in teaching, which I can completely understand, seeing him live in action myself, and in fact drawing a lot of my pedagogical practices from the experiences I've had with Junior. So thanks for that, Junior. In terms of his research prowess, he's an expert in machining and chip formation research, particularly looking at a range of different complex materials across metals, metal alloys. But I kind of slightly turned him more towards the dark side in terms of additive manufacturing, which I use day to day. And so he's now we've been exploring opportunities in that space, looking at machining of additively manufactured metals, polymers, and composite materials. My personal interest is more applied, and I would say Junior complements that quite nicely with his kind of fundamental prowess. And I even tell my students, who I now teach mechanical engineering to, that he was my Yoda, so to speak, and I is Luke Skywalker. Oh, probably don't even deserve the title of Luke Skywalker, to be honest, but there you go. Junior definitely is an expert in that field. And so the research we've been involved in is looking at the fundamentals of build process parameters and how we could look at distinctions that were happening to the build process of additive manufactured polymers when we start to increase layer thicknesses, which was a strategy for reducing print time, but also making large geometry parts, such as the things you'd see in the big area additive manufacturing systems in Cincinnati. more recently, we've taken ourselves to polymeric materials that are elastomeric in nature, applying these to a range of biomedical applications. So looking at diabetic foot and where we can look at the compressive properties of that. And so I've dragged Junior from the other side of the world to aid with some of the fundamental understandings there, which surprisingly haven't been explored too well. So got him in the lab. We're looking at hysteresis in some of those structures that we've made and looking quite topically at design structures known as typically periodic minimal surface area structures as well in that. But I will hand over now before I carry on. Once I'm in my stride, you won't be able to stop me. So without further ado, I'll hand over to you, Junior. Thanks.
Thank you, Iki. You've definitely credited me with too many kind words, which more than I deserve. Thank you, everyone, for giving me the opportunity to come out here. Also, before I start, I'd just like to make a big thank you to the IAS team, Marsha, Kieran, Connor and Sophie and Omar. Thank you for making me feel so welcome. And I've really enjoyed my time here at Loughborough Uni, and no doubt will always remember and be thankful for it. I guess let's get down to this today's talk, which is basically in contrast to what Iki was saying. Additive manufacturing, if we look at my starting out research space is machining, which is the complete opposite of 3D printing. It's what we call subtractive manufacturing. Although there are parallels, which I've observed and reflected with. And I know people who've joined me here today perhaps have different spaces, but perhaps you could draw some similar methodology and parallels, which you might find useful as well. And so the main talk today is to talk about my, God, how long has it been? 13 years in this research space of machining research. So work which I've done in the past in my PhD, moving on as a PhD supervisor, and moving on in my journey, moving towards more current trends of machining research. Okay, so just a bit of introduction of me and where I'm from. AUT University, it's located in Auckland. So if we have a look at the map of New Zealand, it's that red dot right here. It's currently summer, so you can imagine people making snowmen out of sand at the beaches currently, which is very nice and pleasant. I'm not complaining about the weather at UK as well, but it's a great experience. I also love the Christmas markets, which has been quite an experience. Very thankful for that. So yeah, where I'm from, AUT University is a city-based university located in Auckland. If we're talking about population, Auckland is a current population of 1.6 million. It's considered our largest city in New Zealand, which is 5.1. AUT is now considered our second largest university in Auckland, with current enrollments of 27,000 students. 14% of that is international based. The school where I'm from is the School of Engineering, Computer and Mathematical Science. So that's three disciplines, which is engineering, computing science, and mathematical sciences all under one roof, which makes us easily the largest school in the uni. Estimate on numbers in terms of student enrollments Our computing science degree is usually 600 first-year students enrolled, and followed by that, our engineering degree is the second largest with about 200-ish first-year students enrolled. Okay, so that's the background with me, where I'm from. To talk more about machining and where it exists in the New Zealand manufacturing sector. Manufacturing as a whole, these are our most latest figures, which come from our Ministry of Business and Innovation and Employment sector. Manufacturing makes up 24.3 billion, which is 11% of our national GDP. I looked up the current conversion rate, so you just need to divide those numbers by the dollars by 50%, by 2, and you should be able to convert that to the British pound. So yeah, 11% is the manufacturing sector. And the manufacturing sector is made up of different industries. If we focus on the image on the right, in terms of where machining sits in transport, equipment, machinery and equipment. So it makes up about 30% of that manufacturing slice. Yeah, and so for us it's important because it's a big part of our GDP, also employs a whole lot of New Zealanders. And in order for us to remain competitive with the global market, we have to always focus on being innovative with our processes. So research is quite a large part of our business strategy. Video which I'm playing just on machining, put us all in that same context of what I mean by machining. It's a plastic deformation at a very high rate. So it's quite a dynamic process which occurs. You can machine different types of material. Your main focus is you want to try and make the process as efficient as possible and reduce the production costs. So that's all what machining is. Yeah, what my PhD supervisor said to me when he first pitched me to come into the machining space is, when you enter this space, you become a jack of all trades, where you take what you need from, say, mechanical engineering. You need principles of thermodynamics and calculating mechanical work. And then you take what you need from material science principles, and also tribology, which is the science of interacting surfaces, and you apply it to this process of machining to try and generate some new scientific knowledge. So yeah, that's what, in my opinion, machining is. You don't specialize in one. Well, you specialize in machining, but you kind of take what you need from different spaces. So to talk about how do you create a experiment from machining, in terms of general machining research, step one, first step would be to decide what type of machining process you want to create an experiment. If we talk about traditional machining, there are 3 traditional processes. These are drilling, turning, and milling. So for example, let's take drilling, and then we create an experiment out of it. So in this case, we've got a CNC machine, that bright yellow bit which you see in the middle is the drill bit. And it's about to, well, it's set up so it's about to drill into a workpiece, which is, well, you can't really see it, but it's mounted inside this mounting bracket. And the reason why that mounting bracket is there is so that it can literally be connected to this measurement device, which looks like a silver table. That's our dynamometer. And so the whole purpose of this setup is to measure forces required to machine a workpiece material. So yeah, to create an experiment to capture data from a machining process, so you would select the process, second input variable, select the workpiece material. Could be a metal, could be a polymer, could be a ceramic. Different choices to select from. Select the type of tool which you're going to use, because there are different designs of tool material, tool geometry. Looking at coating technology, we have different types of coatings. And then the other three main input variables is going to be selecting your parameters such as cutting speed, feed, and depth of cut. Those last three variables are quite important because they are transferable across the different types of processes, drilling, turning, and milling. So once you've obtained once you've decided on your input variables, the next step obviously would be to collect some data. So in this case, what we have here is an experiment designed to capture cutting forces. We have recorded cutting forces of, in this case, we are looking at machining different alloys of stainless steel. We've got the names designated here: 2507 duplex stainless steel, 2205, and austenitic stainless steel 316L. So what this data can tell you is, if we look at thrust force, which was recorded from that dynamometer, the higher the value in thrust force, the harder it is to cut the material. And as you can see, the blue one, the blue data is showing an alloy which is much more difficult to cut in comparison to the other two, which requires lower cutting force. So it's data like this which we, as machinists or researchers in the machine industry, seek to capture. There are other types of data which we do want to capture as well. Those are going to be based on machining performance, such as measuring surface roughness. It's basically a stylus profilometer, which measures with very sensitivity as the stylus, which is to measure how smooth a surface is after machining. And sometimes the data which you capture doesn't show any good correlation as well, which is an example here, which you can see. But the main, one of the main output variables which you do want to focus on when you are looking at machining is tool wear and tool life. Because cutting tools are very expensive. You do want to optimize your process by selecting which input variables going to give you the best performance in terms of the output variables. And that's basically what I consider as level 1 surface level machining research. And truth be told, you could pretty much make a career or an academic career of publishing papers, just changing input variables, capturing output variables and publishing in a journal or conference paper. Seen this, or you do see this out in the literature and in conferences where people just change the input variables, get different output variables. And I've seen this in parallel when Iki was talking to me this week, where when you go to conferences and you start talking about the process variables which you use for additive manufacturing, and even machining conferences where people from the industry start getting excited and start recording the process variables which you used, because that's the main focus for industry, is to try to optimize these output variables. Whether it's meaningful as whether this is meaningful work as a researcher, I guess it's very subjective and up to the individual. For me, I like finding more challenging, something which is more challenging, and that's trying to get down to the fundamentals. Well, one good thing about this surface level of research is you start to uncover some of the important issues. In this case, when I was looking at machining duplex stainless steel, there was one major issue, which is built-up edge. If we have a look at a zoomed up, so this is a macro view of a cutting tool edge, and that sort of silver bit is material which is stuck onto the cutting tool. You can imagine a piece of gum stuck on the surface. Problem is that that piece of gum stuck on the surface, as soon as it tries to get removed during more cutting, that removal process sort of like picks at the cutting edge. And the main issue is it starts to deteriorate the cutting edge, and it leads to tool wear, which we call adhesion tool wear. Unfortunately, when you do machine duplex stainless steel, it's a very sticky material, so it has a high tendency for this to occur. Still unknown how or why it happens. I came up with an idea, which I'm about to talk about, how I came up with that idea. Up until this day, I don't think anyone's come up with a proper grounding theory as to why this occurs for duplex stainless steel. It continues to be a problem in the industry. People just, well, the way people deal with it is just try and select parameters which don't trigger built-up edge to occur, which is the current strategy to minimize this type of wear occurring. But I tried to focus on determining the why, as to why it happens, because it's kind of like a black box situation where you have input variables and all of a sudden you get these output variables, but you're not sure how it occurred. So what I did was to try and uncover what those output variables, what was happening inside that black box. So to get there, first to talk about what duplex is. it's a two-phase metal, which has equal amounts of ferrite phase and austenitic phase. Each individual phase has, you could imagine, has different types of properties. So that's what the microstructure looks like before you machine it. In a close-up micro view. So what I did was to try and uncover the fundamental reason in terms of trying to figure out why this built-up edge was happening. I looked at an experiment called quick-stop. What quick-stop does is it sort of like pausing the machining process partway through machining, and then what you end up with is a chip sticking out of the workpiece, which is what you see here. It's a very tricky experiment to get done right, but once done right, it does sample. Well, your data sample looks like this. After carefully sectioning it, you can remove it, and then you can cold mount it and prepare it ready for microstructure observation through scanning electron microscope or electron backscatter diffraction, which is what we did. So that's what that's an EBSD map showing how material deforms from the workpiece region and moving up into the chip region. And what we noticed was if we counted and observed where the phases were going during this chip formation process, what we found was there was quite a large amount of ferrite collecting in what we call the stagnation region, which is where built-up edge originates from. So this was a experimental observation. In here you can see running through a phase map. That's what the original microstructure count looks like, and there are clearly larger counts here. So I took that observation and went, this might lead me somewhere, hopefully. And did some more observations from using scanning electron microscope. Did some more EBSD beam time, counting up misorientation angles, and then taking the best knowledge of material science, trying to come up with a working model and explanation as to, well, we've observed there's a huge collection of this phase existing in the stagnation region, taking fundamental material science principles, and this is the model which I came up with, which could possibly explain why there's a collection of one phase which could lead to the triggering of built-up edge formation. And I published a lot of papers too. I was feeling quite hyped and proud of myself, especially with this paper, because I thought I'd solved the problem, and the machining community would welcome me with open arms. Sadly, after 3 years of that publication, only one citation, which was and it was my PhD student. But I guess that's a fact of what can happen, and I guess don't be discouraged of that happening. Some papers you will pour your heart and soul into it. Just have to go with your gut feeling and not regret it. I haven't observed how many citations it is now, but yeah. So that's level 2 of general machining research. Probing more into this subsurface level, trying to come up with models and to explain what are the fundamental causes of important machining issues. Yeah. Sorry, are there any questions, by the way? People are welcome to ask questions while I'm rambling on. Yeah.
So the scanning electron microscopy is basically measuring scanning the surface. How about more in depth? Like, is the chip formation making anything? Like, have you looked at it with atomic force microscopy? For example, to see what happens in an atomic level?
That's a good question. The problem is, are the people able to hear what? Okay. You're absolutely right about scanning electron microscope, only able to observe what's happening in the surface. The main issue is, like, the data which I'm dealing or have to deal with is only one slice of the that chip. And if we look at that chip thickness, it's not very thick as well. So the more you slice it, I mean, I've tried this as well, where I polish a bit of the sample and then observe it under ACM microscope and then polish it again to try and observe that subsurface. I haven't tried AFM though. I did really think that I would find quite a lot of answers using TEM. But again, it's very difficult to try and prepare your sample for TEM. But yeah, I will look into AFM to see if it's.
There's one in our department.
Oh.
Yeah.
Oh, thank you. Yeah, awesome. Any other questions? No. Yeah.
Just for the record, you're on 22 for that paper now, so it's not just.
Oh, 22. Not just my PhD student. Thank you. It's more. I feel better now. It was just waiting process.
Is it the machining action that could be causing a spread of the material?
Machining action?
Yeah, so just scraping the surface, and I'm just kind of trying to think of it dynamically, like all this material kind of being in a secondary phase just at that interface, right? And is it migrating somehow?
Yeah.
That action?
I don't really know. The main issue is it's what we capture is like a static snapshot. What would be ideal is if we had like a video seeing what's happened, which there are videos and ways which people have in a really cool way being able to capture chip formation, which requires very, very detailed and perhaps lots of resources and time and planning. But yeah, I would love to capture duplex in real time, the forming, so that we could answer those problems. I did try and capture real time deformation. Leading into the last and final step of general machining research is modeling. I did try and create a model which was based on the microstructure. So I developed it was a 2D model which could which the mesh shape was based off the two phases. And also I gave the model this corrosion, which was based off that model which I published in that paper, where it tells one phase to start deforming rapidly after a certain strain rate. And then was able to run that model, and it was not gonna, I'm actually running a workshop to, I figured I wouldn't have time to explain this model here during this lecture, but I'm running a workshop next week to explain how this model was formed. But you can, it is also published in the paper. So if you are interested in learning how a model like this can be developed, full details is published in that paper there. But yeah, we managed to get good, you could say, good correlation in terms of stresses, von Mises stresses and strains to what we observed experimentally, and also the shape of the chip which was generated from the model. We're able to get good correlation between virtual and experimental data. Okay. So those were basically, well, what I considered 3 levels of machining. First one, machinability. Machinability studies, which is happening at the very surface, where you have input variables, which is parameters, and you get output variables, which is performance. But that level is good for publishing. Also helps identify machining issues. And that leads into the second level, which is characterizing machining issues. So find what are the causes of these, or what are the fundamental triggers which causes these issues. And then level 3, to try and model and replicate what you see physically. Yeah, so that's pretty much my research for the past 13 years. I've moved on to also other different metals, primarily focusing on metals which are difficult to machine. That's very much been myself and my group's main focus back at AET. Moving on to the, I just want to talk about 2 current trends, which is very popular in our industry in New Zealand, and where I've got PhDs assigned on. The first one, finely cutting solutions for super light materials. Feel like the industry, especially transport sector, is moving, well, has been and still moving in using super lightweight materials. So these could include composite materials, carbon fiber, glass fiber, even metal matrix composites. Other lightweight metal alloys, magnesium, TI-64 continues to be an issue, machining issue, which people publish numerous papers year by year. And just to paint a picture of it being used in industry, is an example of 747 and the split of different materials being used. And as you can see, 50% of the aircraft is made from composite material. If we have a look at, the first challenge with machining composite material, if we have a look at the different types of composites, for example, we see laminar, we have discontinuous composite materials such as particle reinforcement flakes. So these are little fibers which have been, you could imagine, probably not sprinkled, and then in comes the polymer to cover it. So discontinuous, and then we've got continuous woven fibers, which can be unidirectional or 45 or single direction. So the first challenge with machining composites is the last thing you ever want to do is to put a hole in it, which is kind of like, so what do? The reason why you never want to put a hole into a composite material is because you ruin the structure, the internal structure. But ultimately you will have to put in a hole into a composite component, as you know, for situations when you can't make the composite out of one complete piece. You have to join two composite components together. So, yeah, when you machine composites, it causes subsurface damage, delamination, fiber fracture, all those terrible words which you don't want to hear as an engineer. And so you want to try and minimize those effects as much as possible. If we have a look at Auckland, and if you didn't know, Auckland's nickname is the City of Sails. Got a huge maritime industry in Auckland. And so we're looking at partnering up with this company here, which they construct super yachts, and they work with Kevlar, also glass fiber and carbon fiber. But ultimately what they have to do is they have to drill holes. And that's a hole, as you can see there are 4 holes. Some of these holes are quite large. Sometimes can be as large as 100 mil in diameter. And if you think of composites, it's very rock hard. It's almost like trying to drill into concrete, which in terms of how hard composite material is. So you can get excessive tool wear quite fast. And drill tools for composite materials are very, very expensive. Single drill tool would cost about 1,000 New Zealand, which is 500 pounds. So you want to make that last as much as possible. Here's some data collected, which shows, how volatile tool wear can get quite fast when you are drilling composite material. So here we have time, and it doesn't take long for tool wear to progress. Usually tool wear is, as soon as your cutting tool edge wears by 0.5 millimeters, which is very, very small. But you can imagine when it gets to 0.5, it's like trying to cut with a blunt knife. So, tool wear happens quite fast when you are machining composite material. So, I've got one PhD student trying to collect data at the moment, working with composite material, and go through that process of collecting machinability data, trying to identify what are fundamental issues and trying to come up with a better cutting solution than what's current. Second to last slide and last topic in terms of trend. Got another student who's going to be working on developing AI technology for machining of difficult materials. So here's an example of a schematic of a proposed deep learning model. So yeah, and I've also got a lecturer from the computing science department who specializes in AI, which is very handy because my coding is very terrible. The main focus here would be to try and develop a working AI model which can be trained using live or past experimental data which can be fed into the AI model, and hopefully that AI model can select input parameters which will then optimize some of those output variables which you saw in the first slide. And that's where I'm currently at. That was my last slide. Thank you.